triggering air temperatures causing high levels of urban heat island effect due to high density population, transportation and buildings emitting massive amount of heat into the atmosphere. The building sector, with uncontrollable dependency on services like air conditioning, lighting, refrigeration, etc., is claimed to be one of the biggest energy consumers, consuming nearly 40% of the global energy, along with emitting around one-third of all greenhouse gases. Additionally, the rate at which fossil fuel energy is currently powering the building sector, studies are reporting a gradual decrease in the fossil fuel source, and have also highlighted fossil fuels to vanish in the next 55 to 113 years. The reduction of the building energy consumption and dependency on fossil fuel energy stands as the highest priority for the UAE government, predominantly due to UAE's building sector consuming nearly 70 to 80% of the country's total generated electricity. With increasing population, rapid climate change, and severe depletion in fossil fuel energy, the demand for renewable-based energy generation is increasing rapidly. Consequently, UAE is at the forefront for altering the trend towards dependency on renewables in alignment with initiatives at the international level such as the United Nations Sustainable Development Goal 7 of access to affordable and clean energy, and local levels such as Dubai's Clean Energy Strategy 2050, where Dubai aims to increase 75% of clean energy share by 2050. UAE is constantly working towards this goal not just through solar power and nuclear energy, but also through wind energy, though the region experiences low wind trends. As a first step, UAE installed the region's first wind turbine on the Sarbanias island, having a production capacity of 850 kW per hour. Over the years, wind turbines have drastically evolved from traditional turbines. Currently, there are two major operational types of wind turbine technologies that can be used towards building applications. These are classified into vertical axis wind turbines and horizontal axis wind turbines. Even after the application of these improved turbine designs, wind turbines were not able to reach the predicted efficiency. So there was a need to focus more on the efficiency and less complex concept to result in investing more towards wind energy to augment more turbine power, especially in the case of horizontal axis wind turbines. There was a need for a new and efficient type of wind turbine in the industry, along with its application in small housing rather than focusing only on large-scale buildings, which led to the introduction of the concept Diffuser Augmented Wind Turbines, also known as DOT. The diffuser augmented wind turbines were introduced to increase the efficiency of the wind turbine by having the turbine enclosed by a duct-like shroud. In recent years, several studies have been conducted in the development of the DOT and its concept, particularly in having an optimal design of the shroud in the wind turbine and for determining different strategies to accelerate wind speed and generate required energy. The enhancement in the performance of the DOT depends on various factors such as the shape of the diffuser, geometries, blade airfoils, and wind conditions at the site of installation. The geometric features are the key parameters in deciding the aerodynamic performance of the wind turbine. Each one of these parameters has a direct or indirect effect on the performance of the DOT. Various literature has highlighted the design alteration of introducing curvatures in the interior of the turbine and reducing the area of the airflow to cause higher pressure drops. Consequently, velocity increases with the decreasing area if the flow rate is constant. Considering this design principle, our research aims to test various geometries to attain optimal performance of a DOT, especially in low wind regions such as UAE.
In alignment with the research aim, the research methodology involved designing 4 different wind turbine geometries with varying parameters in a 3D modeling software and analyzing it through computational fluid dynamics software. Solid Edge was utilized as the parametric solid modeling software for the experimental process. Solid Edge is a user-friendly software which can easily be exported into ANSYS CFD for further simulations. A total number of 4 models were used for the comparative analysis. All the models are created following the Venturi principle, having bigger entry openings and comparatively smaller diameter for the exit openings. The first diffuser for the comparative study has a conventional shape which is typically employed in the industry. The cross-section and visual representation of the model is as follows. The second diffuser has a straight, smooth external surface with comparison to the first one, while the interior surface has a protrusion similar to that of a flower. The cross-section and visual representation of the model is as follows. The third diffuser has a pattern mimicking the shape of a flower both on the internal and external surface of the model. Additionally, few holes of similar sizes are provided to experiment the influence of holes on velocity and pressure. The fourth diffuser has a unique configuration in comparison to the other three models. The fourth model has significant decrease in the thickness and length of the model. Additionally, the diffuser also has added material around the exit diameter to check if the pressure drop would significantly increase due to vortices around the free edge of the fourth model. The four model shapes were then exported to ANSYS computational fluid dynamics software to carry out the simulations. Before the extraction of the results, the models were processed through steps such as mesh generation and assigning of required boundary conditions. Meshing is an essential intermediate step that influences accuracy of results. The model showed positive results at resolution value of 7, and the inflation boundaries was set to program control with a tetrahedron mesh which fit in complex geometries than any other types of mesh. Under the boundary condition, 3.5 meter per second was assigned as the inlet speed for each simulation in accordance to the average mid speed in the UAE. The maximum diameter for efficient simulation was kept as 100 mm with the y-axis as a constant axis of revolution. The inlets and outlets for each simulation were placed on the exit planes on either side of the diffuser. Iterations were conducted through hybrid initialization and calculation where the values were converged between the range of 50 to 150 depending on the geometry of the models.
The results and analysis of the study are done through a comparative analysis between the four shapes of turbines focused on the observed pressure losses and subsequent acceleration in wind speeds through each of them. A sophisticated methodology was put into place to observe the parameters within the confines of the turbine. The identities of the turbine were classified numerically with the provision of a single word description of its shape. Subsequently, lines were plotted at the entry, middle, and exit on an axial plane, and a radial line was plotted across the cross section of each turbine to enable the collection of data along these lines. Velocity streamlines are shown through 200 data points on a 2D plane from the top of each turbine and an axonometric view to understand the scope of acceleration. Graphical comparison between the first two turbines D1 and D2 signifies that D2 achieves higher acceleration. Since the minimum average velocity of 3 meters per second is attained by ambient average wind speeds in the UAE, the percentage increase in velocity is given more importance. Therefore, through data analysis, D1 and D2 achieve 22.78% and 57.24% increase in maximum velocity. Similarly, the graphical comparison between D3 and D4 signifies a higher acceleration in D4 by 35.49% and 45.83% respectively, as shown in the illustrations. The comparative analysis of velocity signified that D2 and D4 perform most efficiently among the four turbines. Therefore, the pressure losses across the length of the turbines on the radial data line plot were determined as shown in the chart below. The average pressure loss in the central plane of D2 and D4 are shown in the figures to illustrate the area of pressure losses due to the turbine's geometry. D2, due to its longer length, has higher pressure losses for a larger area in comparison to D4. This is reflected in the velocity comparison, wherein D2 and D4 have augmentations of 57.24% and 45.83% respectively. Although the principles behind all the geometries remain the same, the inventive shapes of D2 and D4 have performed well under simulative conditions. Their velocity contours during entry, Initial augmentation and constant augmentation are shown in the figures and will determine the plane of fan placement for the most efficient augmentation. These simulations can further be developed for these shapes to be polydirectional and achieve even greater augmentation.